Welcome everyone. I'm excited to kick off this presentation on probability. Today, we'll explore what probability is, why it matters, and how it applies to real-world situations. We'll cover some key concepts and practical examples to help you better understand this fascinating topic. Let's get started. Let's start with the concept of an elementary event. An elementary event is the most basic possible outcome of an experiment. For example, when you flip a coin, getting heads or tails are elementary events. Each outcome is simple and cannot be broken down further. Next, we look at probability from an experimental approach. This means we find the probability of an event based on actual experiments or trials. Instead of just guessing, we observe how often an event occurs over many repetitions. Now, it's important to understand some basic terms related to probability. Terms like event, which is any outcome or set of outcomes we are interested in, and sample space, which includes all possible outcomes of an experiment. Recognizing these terms helps us communicate clearly about probability. Moving on, an example of probability can really clarify things. Say, rolling a die. The probability of rolling a 4 is 1 out of 6 because there are 6 possible outcomes, and only one of them is a 4. This helps us see how probability measures likelihood. Then we encounter different types of events. For example, independent events, where one event doesn't affect another, and dependent events, where outcomes are linked. Understanding these types is crucial for calculating probabilities accurately. Finally, understanding events in probability is about recognizing how different outcomes relate and how we can analyze their likelihood. This understanding forms the foundation for introducing the broader concepts of probability, which we'll explore further as we go along. All of these points build toward a comprehensive understanding of probability, starting from basic events and moving toward more complex ideas. Welcome to our introduction to probability. Today, I want to start by explaining what probability really is and why it matters. At its core, probability is all about quantifying uncertainty, how likely something is to happen. It helps us make sense of the randomness we encounter daily, whether we're predicting weather, analyzing sports outcomes, or making business decisions. Understanding probability gives us a framework to assess risks and chances in a logical way. This slide is foundational because, as we progress, you'll see how probability underpins many statistical methods and real-world applications. So, keep in mind that grasping these key concepts now will really strengthen your overall understanding moving forward. Probability is fundamentally the study of uncertainty. It helps us understand and quantify situations where outcomes are not certain or fixed. Whenever we face a doubtful or unpredictable scenario, probability provides the tools to measure just how uncertain that situation is. By doing this, we can make more informed decisions, even when the future isn't clear. This concept is central to many fields, from statistics and finance to science and everyday life. So, as we move through this presentation, keep in mind that probability is all about grasping the chances or likelihoods of different outcomes, helping us navigate uncertainty with a bit more confidence. Now, let's take a closer look at the various uses of probability across different fields. Starting with weather forecasting, probability helps us predict weather conditions by analyzing patterns and statistical data. It allows meteorologists to estimate the likelihood of rain, storms, or sunshine, which is crucial for planning and safety. Moving on to biological sciences, probability plays a key role in evaluating the chances of genetic traits being passed on, helping us understand inheritance and variation. In physical sciences, analyzing the behavior of particles relies heavily on probability models to understand phenomena at a microscopic level. In medical sciences, probability helps determine the effectiveness of treatments by analyzing clinical trial data, guiding healthcare decisions. When we look at commerce, probability is used to assess market trends and consumer behaviors, enabling businesses to make informed decisions and strategize effectively. Finally, in mathematics itself, probability underpins the ability to understand and quantify risks, making predictions about uncertain events. Connecting all these points, the overarching theme is that probability provides a powerful framework for understanding and predicting outcomes across diverse disciplines. It's truly a foundational tool that helps us make sense of uncertainty in our world. Let's take a moment to go over some basic terms related to probability that will help us understand the concepts better. First, we have the idea of an asterisk probability asterisk, which is simply a measure of how likely an event is to happen. Think of it as a scale from 0 to 1, where 0 means the event cannot happen, and 1 means it is certain to happen. Next, we often talk about asterisk sample space asterisk, which is the set of all possible outcomes of an experiment. For example, when flipping a coin, the sample space includes heads and tails. Understanding the sample space helps us see what outcomes are possible and how to assign probabilities to each. Then there's the concept of asterisk events, which are specific outcomes or groups of outcomes within the sample space. For instance, getting a head in a coin flip is an event, and so is getting a tail. Events can also be more complex, like rolling an even number on a die. Finally, it's important to grasp asterisk probability models, which are mathematical frameworks that help us calculate and predict the likelihood of different events. They're essential tools that connect the basic terms to real-world applications. These foundational concepts are key because they form the building blocks of understanding how probability works, and they tie directly into the broader theme of making informed decisions based on likelihoods. Now let's talk about what we mean by a random experiment. Essentially, if you're conducting an experiment and you don't know in advance what the next outcome will be, then you're dealing with what we call a random experiment. The key point here is the element of unpredictability. Each time you perform the experiment, the result could be different, and you can't precisely predict it beforehand. This concept is fundamental to understanding probability because it sets the stage for analyzing situations where outcomes are uncertain. So, whenever you're in a scenario where the next result isn't guaranteed and could vary, you're working within the realm of a random experiment. This idea helps us grasp how probability models real-world situations where outcomes are inherently uncertain. Let's take a closer look at some simple examples of trials, starting with tossing a coin. When you toss a coin, there are only two possible outcomes, heads or tails. Each toss is considered a trial because it involves performing an action, throwing the coin, and observing the result. Next, consider throwing a dice. When you roll a standard six-sided die, the outcomes are the numbers 1 through 6. Again, each roll is a trial because you're performing an action, throwing the die, and the result is one of those possible outcomes. The key idea here is that a trial is any action where the result can be one or more outcomes. It's like a test. You perform the action, and the result is the specific outcome that occurs. This concept is fundamental because it helps us understand how to analyze and predict the likelihood of different results in various experiments or games of chance. By understanding what constitutes a trial, we lay the groundwork for exploring the probability of different outcomes, which is essential in the broader study of probability theory. Let's take a closer look at understanding events in probability. When we talk about events, we're referring to specific outcomes or sets of outcomes within a probability space. It's important to identify these events clearly because they form the basis of calculating probabilities. Sometimes, events can be simple, like flipping a coin and getting heads, but other times, they can be more complex, involving multiple steps or conditions. Recognizing how events relate to each other, whether they are independent, mutually exclusive, or overlapping, helps us better understand how to approach probability problems. This understanding connects directly to our overall goal of making informed predictions based on chance. So, grasping these concepts of events is fundamental in mastering probability theory and applying it effectively. All right, so let's consider throwing a die. When we do that, the possible outcomes include numbers from 1 to 6. Now, if we're focusing on the even numbers, there are 3 of them, 2, 4, and 6. This means that the event we're interested in, getting an even number, comprises 3 outcomes. It's important to understand that an event in probability is basically a collection of some specific outcomes of an experiment. So, in this case, the event, getting an even number, consists of those three outcomes, 2, 4, and 6. Connecting this to our overall theme, recognizing what constitutes an event helps us analyze and predict different scenarios in probability. It's a fundamental step in understanding how likely certain outcomes are when we perform experiments like rolling a die. Let's take a closer look at the concept of probability from an experimental perspective. When we talk about probability in this way, we're focusing on actual experiments or trials to understand the likelihood of different outcomes. This approach emphasizes observing real data rather than relying solely on theoretical assumptions. For example, if we flip a coin many times, we can record how often it lands on heads versus tails. Over time, this experimental method helps us estimate the probability of getting heads. The key idea here is that by conducting repeated experiments, we gather empirical evidence that informs our understanding of chance. This experimental approach is especially useful because it connects directly to real-world scenarios. Instead of abstract calculations, we're examining what actually happens in practice. This makes the concept of probability more tangible and applicable. Overall, thinking about probability experimentally allows us to see the connection between theory and actual outcomes. It encourages us to base our conclusions on observed data, which is a fundamental aspect of scientific investigation and decision-making. So, if the total number of trials is n, then the probability of event D happening is calculated based on the outcomes we observe from these experiments. Essentially, experimental probability is derived from actual trials, meaning we look at what actually happens during our experiments rather than just theoretical predictions. The key idea here is that this probability depends on two main factors: the number of trials we conduct and how many times the event we're interested in actually occurs. By observing these outcomes, we can estimate the likelihood of event D happening in real-world situations, which makes this approach very practical and grounded in actual data. This connects to the overall theme of understanding probability through experimentation, helping us see how real results inform our expectations about future events. All right, let's walk through this slide. First, we want to check whether the sum of the two probabilities, getting heads and getting tails, equals 1. This is fundamental because, in probability, all possible outcomes should collectively cover the entire sample space. Next, we look at finding the probability of getting tails. Since we tossed the coin 100 times and got 51 tails, we can calculate this probability by dividing the number of tails by the total number of tosses. Similarly, for heads, we divide the number of heads, which is 49, by 100. This gives us a clear picture of the likelihood of each outcome based on our experiment. It's important to note that these probabilities should add up to 1, confirming that we've accounted for all possible outcomes. This example helps illustrate how empirical data aligns with theoretical probability, reinforcing the idea that probabilities are always between 0 and 1, and that their sum for mutually exclusive outcomes should be exactly 1. Now, let's take a closer look at the different types of events. When we talk about events, we're referring to specific occurrences or incidents that can happen within a system or process. These can vary widely, but understanding the key types helps us better manage and respond to them. First, there are *** scheduled events **, which happen at predetermined times or intervals. Think of things like regular maintenance or routine reports. These are planned in advance and help us keep the system running smoothly. Next, we have **unscheduled events **. These are unexpected and often urgent, like system crashes or security breaches. They require immediate attention and often trigger alerts or emergency protocols. Then we also encounter **triggered events **. These occur when specific conditions are met, such as reaching a threshold or an anomaly being detected. For example, if CPU usage spikes beyond a set limit, that's a triggered event. Finally, some events are **manual events, initiated by a user or administrator. These might include starting a backup or executing a script. Understanding these different types is crucial because it influences how we monitor, respond, and automate our systems. Recognizing the nature of an event helps us prioritize actions and ensure system stability, which ties back to our overall goal of effective management and resilience. While doing a test, if an event is not possible to occur, then its probability will be 0. This means that the event cannot happen under any circumstances. We call this a completely impossible event. For example, trying to roll a 7 on a standard 6-sided die is impossible because it simply cannot happen. The key point here is that probability measures the likelihood of events, and when something is impossible, its probability is 0. Recognizing impossible events helps us understand the boundaries of what can and cannot happen in any situation. This concept ties back to our overall theme of understanding probabilities and how they help us predict and analyze different outcomes accurately. So let's consider this example of an impossible event. You cannot throw a standard 6-sided die and get a 7. It's simply not possible because the die only has the numbers 1 through 6. This highlights a key point. Some events are impossible within certain frameworks or conditions. By understanding what makes an event impossible, we can better grasp the concept of probability. It's important to recognize these impossible events because they help us define the boundaries of what can and cannot happen in a given situation. In the context of our overall theme, identifying impossible events sharpens our understanding of probability and helps us distinguish between unlikely and truly impossible outcomes. Let's talk about what happens when we're absolutely certain that an event will occur. In probability, this is called a sure or certain event. Essentially, it means that the likelihood of that event happening is 1. When we say the probability is 1, we're indicating complete certainty. There's no doubt at all that the event will take place. This concept is important because it helps us understand the full spectrum of probability, from impossible events with a probability of 0 to certain events with a probability of 1. Recognizing sure events allows us to better grasp how probability models real-world situations where some outcomes are guaranteed. This slide shows that the probability of an event could be anywhere between 0 and 1, so we write it as 0 less than or equal to P of E, less than or equal to 1. This range makes sense because a probability of 0 means the event cannot happen, and a probability of 1 means it is certain to happen. For example, if we have a bag that only contains blue balls, then it is certain that if we draw a ball, it will be blue. This is what we call a sure or certain event. Understanding these concepts helps us grasp the basics of probability, especially when we're dealing with events that are guaranteed or impossible. It ties into the overall idea that probability measures how likely an event is from impossible to certain. All right, let's take a look at this slide. We're focusing on the probability of seed germination, and specifically on the different scenarios based on the number of seeds in each bag. First, we have a question about bags that contain more than 35 seeds. Then, there's the case of a bag with exactly 49 seeds. And finally, we're looking at bags with more than 40 seeds. The main idea here is to understand how the number of seeds in a bag influences the likelihood of germination, especially when we select seeds at random. In this example, we have 5 bags, and we've taken 50 seeds from each one to see how many actually germinated after 20 days. The recorded germinated seeds are 40, 48, 42, 39, and 41 for bags 1 through 5 respectively. What we want to understand now is, based on these observations, what can we say about the probability that seeds from these bags will germinate? This ties back to our overall theme of probability and how real-world data, like these germination counts, help us estimate that probability. So, by analyzing these numbers, we can get a better sense of the likelihood of germination under different seed count scenarios and improve our predictions for future seed batches. So the required probability here is 5 divided by 5, which equals 1. This means that in all 5 bags, the event we're considering always occurred. Moving on, we see that the number of bags in which more than 35 seeds germinated is 5. Since all 5 bags had more than 35 seeds germinate, the probability of germination of 49 seeds in a bag is 0 divided by 5, giving us 0. Essentially, no bags had as many as 49 seeds germinate. Next, we look at the number of bags where exactly 49 seeds germinated. That count is 0. So, the probability of germination of more than 40 seeds in a bag is calculated as 3 divided by 5, which equals 0.6. Finally, the number of bags where more than 40 seeds germinated out of 50 seeds is 3. These calculations help us understand the distribution and likelihoods of seed germination across the different bags, which ties into our overall theme of analyzing probabilities in biological experiments. Now let's take a closer look at what we call an elementary event. In probability, this is the most basic possible outcome of an experiment. Think of it as a single, indivisible result that can't be broken down any further. For example, flipping a coin and getting heads is an elementary event. It's simple, straightforward, and forms the building blocks for more complex probability calculations. Understanding these elementary events is crucial because they help us define and analyze the larger, more complicated events we encounter in real-world scenarios. By grasping these basic outcomes, we set a solid foundation for understanding how probabilities work in various contexts. Now let's talk about P, H, and P not H. These are what we call complementary events. Essentially, if the probability of event H happening is some value, then the probability of H not happening is just 1 minus that value. In other words, P, H minus 1 equals P not H. And since all probabilities must add up to 1, we have that P, H plus P not H equals 1. Similarly, if we consider another event T, the probability of T occurring plus the probability of T not occurring also sums to 1. This brings us to the general idea that if we add up all the elementary events in an experiment, that is, all the possible outcomes, their total must be 1. This is a fundamental principle in probability. Now, a quick remark. If an event has only one possible outcome, meaning there's just one way it can happen, that's called an elementary event. It's like a basic building block in probability, representing a single, specific outcome. Understanding these concepts helps us see how probabilities are interconnected and why their total always sums to 1, which is key to analyzing any experiment or chance process. Let's look at an example of probability in action. Here, we're illustrating how likely an event is to happen based on certain conditions. When we talk about probability, we're essentially measuring the chance of a specific outcome occurring. This slide highlights how we can quantify that chance with real-world examples, making the concept more tangible. Understanding this example helps us see how probability applies beyond theory, impacting decision-making and predictions in various fields. By grasping this, we reinforce the overall theme that probability is a powerful tool for understanding uncertainty and making informed choices. Let's consider a real-world example to understand probability better. Suppose a batsman plays 30 balls in a match and hits a boundary, which is a 6 times. Now, what we're interested in is finding out the probability that he does not hit a 6 in any of those balls. First, we look at the total number of balls played, which is 30, and the number of times he hits a 6, which is 6. From this, we can estimate the probability of hitting a 6 on any given ball, which is 6 divided by 30. That simplifies to 1 over 5, or 0.2. So the probability of asterisk not asterisk hitting a 6 on a single ball would be 1 minus that, which is 1 minus 0.2, giving us 0.8. This means there's an 80% chance that he doesn't hit a 6 with any particular ball. Now, to find out the probability that he doesn't asterisk hit a 6 in all 30 balls, we raise this probability to the power of 30. That is 0.8 raised to the 30th power. Calculating this gives us the likelihood that the batsman stays 6 free across all those balls. This example illustrates how probability allows us to quantify uncertainty, predicting the chance of specific outcomes based on observed data. It's a powerful tool, especially in sports analytics and many other fields, as it helps us make informed predictions and understand risks. Thank you, everyone. So, to find the probability that the batsman does not hit the boundary, we'll base our calculations on the outcomes we've discussed earlier. Specifically, we'll look at how many times he hits the boundary versus the total number of balls he played. In this case, the total number of balls faced is 30. Let's define D as the event of hitting a boundary. From here, we can analyze the data to determine the likelihood of that event occurring or not occurring. This helps us understand the overall batting performance and the chances of avoiding boundaries in future deliveries. The key takeaway is that by understanding the number of boundary hits relative to total balls, we can estimate the probability of not hitting a boundary. This kind of analysis is fundamental in cricket statistics, as it allows us to make informed predictions and evaluate a player's consistency. Thanks again for your attention.